So following up on the example of elastic and plastic section modulus for rectangular sections, we'll now look at the elastic and plastic section properties for I-beams, or W sections, wide flange sections. There's a number of different names for them. In Canada, we typically refer to these as a wide flange section or a W section. Now, a W section has a doubly symmetric shape. So we have a flange and a web and another flange. And we know from our studies and somewhat intuitively that a neutral axis exists right in the middle for double symmetry. And we can say that this is at location y and y. This section has a height of d, a width of b, a flange width of tf, a web width of w, and the same flange width up here, the same flange width of tf. Now, if we were to apply a moment to this section, we'd end up with a strain, and using the assumption that plane strains remain plane, which is a very valid assumption, especially for flexural bending or for beam bending like this, we end up with a strain distribution that has a strain at the top, which is less than or equal to yield strain if we can remain elastic, and the strain at the bottom, which is also less than or equal to yield strain. And if we now go and look at our material property here, we have strain and stress, and if we have an elastic perfect plastic behavior, we can get a yield stress and a yield strain, and we're saying that the strain everywhere is in this linear region. This would result in us having a stress distribution that would also be linear. And we'd have stress at the top is less than or equal to Fy, and stress at the bottom is less than or equal to Fy. So we have linear strain and linear stress. This is elastic. We saw before that we can jump through this elastic section stuff pretty quickly by, instead of going through first principles where we calculate forces within our flange and our web and use moment equilibrium and force equilibrium, we can instead jump to the equation where we know that stress is equal to moment times y over moment of inertia, or conversely, moment is equal to stress moment of inertia over y. And we also did define that that's equal to stress times section modulus, where section modulus is I over y. So how do we calculate I for this thing? Well, there's a number of different approaches to this, but since we know we have all this symmetry happening in the neutral axis right in the middle there, it's pretty easy to calculate the moment of inertia of the rectangular block and then subtract from it the moment of inertia of the two sections that aren't there between the web and the flanges. In other words, we can take I is equal to 1 over 12 multiplied by b d cubed minus b minus w times d minus 2f cubed. So here you'd see that we're taking a rectangle, the entire thing, minus a rectangle comprised of the two sides. And since they both share the same neutral axis, we don't need to apply parallel axis theorem. And if we were to compute this out, we would end up with the ability to directly calculate our section modulus for this shape. It's a bit easier for us to look at this as an example that we'll get to in the next step. So before we do that, at this point we're able to, now we can find section modulus. Let's call that moment of inertia with x. So we can find that. We can find moment yield is equal to Fy section modulus, so we can find that. So it's just a matter of doing the computation by plugging in some values at this point. So let's move on to the plastic properties for that shape, as the elastic weren't all that interesting. So the plastic shape properties. Well, now we have the same section, so we have the same I-beam, or W section, the same geometry. We have D still. D is the entire height of that, and we have B and TF and W. And since it's symmetric, since it's doubly symmetric, or at least symmetric about the x-axis here, we know that the plastic section modulus, or the plastic neutral axis, will be at the same location as the elastic neutral axis, which is right in the middle. So y is equal to d over 2. And if we were to apply a moment to this thing, now let's apply plastic moment, MP, and draw our stress distribution and our strain distribution. Let's start with strain. We would get an epsilon at the top, and now we'd say that much, much greater than epsilon y, and an epsilon strain at the bottom is much, much greater than yield strain, to the point that effectively everywhere in the section has plastified. Now recall we have a stress-strain distribution that we consider elastic perfect plastic. In other words, we have this elastic region, goes up to epsilon y, and then it follows a plastic plateau indefinitely with a magnitude of yield Fy. And if that's the case, if the strain is much, much larger, way over off in infinity region, we end up with this plastic stress blocks. 2 rectangular stress blocks of magnitudes Fy on top and on bottom. So we know that to be the plastic stress and plastic strain distribution. Let's zoom in a little bit on this stress block itself. And if we come down here and look at it, we can draw it out. And we see that we are at magnitude Fy at both locations. We have this moment. We have a height here of y. And we have a force in the top flange, F flange top, and we have a force in the top web, F web top, and a force in the flange bottom, and a force in the web at the bottom. And we know the magnitude of the top flange is going to be the area of the flange multiplied by the stress. So it's going to be B TF multiplied by Fy. And the area of the bottom flange multiplied by the stress, B TF Fy, is Fb. Now Fw, the force in the web between the neutral axis and the top flange, is the area of this web multiplied by the stress. So that will be, the area will simply be d minus the flange thickness divided by 2 multiplied by w. So this is the area. D is the whole height minus 2TF. D minus 2TF divided by 2 multiplied by W is the area of that section. And to that we multiply by Fy. And at the bottom we end up with D minus 2TF all over 2 times W multiplied by Fy again. So now we can solve for the value of the plastic moment by taking the sum of moments about this neutral axis location. We call that the plastic neutral axis. If we take the sum of moments about the plastic neutral axis and set that equal to 0, we'd end up with MP, and I drew it as going this way, is equal to F flange top times Y flange top going in that direction, plus F web top times Y web top, rotating counterclockwise, plus F flange bottom times Y flange bottom, still the same direction, plus F web bottom times Y web bottom. And then we can simplify this by saying that we just determined that the web at bottom and web top forces are the same, and the flange bottom and flange top forces are the same. So we could say FT is equal to FB, and F web top is equal to F web bottom. This allows us to simplify this slightly and say our plastic moment is simply equal to 2 times our force in the flange times our flange moment arm plus 2 times our force in the web times our web moment arm. And if we look at the distances involved in this, we can say that our Y for the flange at the top is going to be equal to D minus D over 2 minus TF over 2. In other words, let's go back to our drawing. We have the whole height divided by 2, which gives us the height from here to here, minus the flange thickness over 2. And that's the centroid of the flange force. And the Y for our web at the top is simply equal to D over 2 minus TF, all divided by 2. Now, if we define plastic moment is equal to, as we calculated up here, we've found a way to calculate plastic moment. We could also define plastic moment is equal to Fy times Zx. So we're defining plastic section modulus. Zx is equal to mp over Fy. Where the x is about the x-axis. And we recall that we had a shape factor k is equal to the shape factor, and this is equal to z over s. So with that solved here, we've effectively found a way to calculate our moment, and then now that we know our moment, we can back calculate our section modulus and our plastic section modulus and compare it with our elastic modulus. So to do that, let's look at an example. Let's put some numbers behind this. And here we'll draw an I-beam out, a W section. And we'll give it the flange, thickness of the flange, thickness of the web, or just W, sorry, the flange thickness, B, and D. And once again, we have these elastic, perfect plastic properties, epsilon and strain, and we end up with off into infinity at Fy. And here we have yield strain and yield stress. So we can say that for this example, we had TF, flange thickness of 20 millimeters. We had a web thickness of 10 millimeters. B is 200 millimeters. D is 400. And Fy is 350 MPa, megapascals. And we are tasked with the following. We want to find My and Sx, the elastic section modulus. We want to find MP and Zx. And finally, we want to find the shape factor. And we know that this is equal to K. So to do this, we'll simply follow what we've already defined. Start with calculating our moment of inertia, our elastic material property, Ix, or elastic shape property there. Ix is 1 over 12 times B d cubed minus B minus W times D minus 2TF cubed. And this is 1 over 12 times 200 times 400 cubed minus 200 minus 10, this is B minus W, times 400 minus 40 cubed. So the elastic property for moment of inertia is equal to 327.95 times 10 to the 6th millimeters to the 4th. I shouldn't have crossed that out, I meant to underline it. And now we can directly calculate section modulus is equal to I over Y, and this is equal to 327.95 times 10 to the 6th millimeters to the 4th over D over 2, which is 400 over 2. And we come up with section modulus is equal to 1639.7 times 10 to the 3 millimeters cubed. So that's the elastic property done there. And then we can compute moment is simply equal to, yield moment is equal to Fy times section modulus, and that's 350 MPa multiplied by our section modulus, 1639.7 times 10 to the 3 millimeters cubed. And we end up with My is equal to 573.9 times 10 to the 6th Newton millimeters, which is 573.9 kilonewton meters. So if we might as well circle the good stuff in red. So we found the first part of this problem was the elastic properties pretty easily. Now our next task would be to find our plastic properties, and here we want to find our plastic moment. That was elastic, so now let's go to plastic. And we'll just quickly sketch this out. By the time we're done this, you'll see how handy those tables are, because it saves a little bit of effort in calculating if we don't need to find this Z value. So if we apply to moment, And that gave us this stress that's two rectangular stress blocks. And this magnitude of that stress is Fy is equal to 350 on top and bottom. And we had a force in the flange and a force in the web and a force in the web and a force in the flange. And we already know that those values are equal to each other from what we looked at just earlier. And if we carry out our plastic neutral axis over here, we can say that we have some distances there. And this is YW. And we also have distance to our force in our flange, Y flange. But we define our force in our flange is equal to the area of the flange multiplied by the stress in the flange. We end up with Fy times Tf times B. So we can plug in some values for that and get 350 MPa multiplied by our flange thickness, which was 20 millimeters, times B of 200 millimeters. And we end up with our flange force is 1260 times 10 to the 3 newtons. Now we can compute our web force the same way. Our force in our web is equal to A web Fy. So A web on top of the neutral axis and below the neutral axis. We might as well go A web over 2 because half of it's below and half of it's above. And this is equal to Fy times W times D minus 2Tf all over 2. And if we plug in some values, we get Fw is equal to 350 MPa multiplied by 10 millimeters is W, multiplied by 400 minus 2 times 20 over 2. Pardon me. And this gives us Fy, or Fw, the web force, is equal to, oh, I made a mistake up here. This was, let me just strike this out here. This was Fw, a transcription error here. So Ff was 1400. And Fw was 1260 times 10 to the 3 newtons. So now that we have those values, and I might as well just underline them so it's getting a little bit messy here. We have those two values. We need to get the moment arms for those values, YW and YF. Now YF is not hard to find. That's simply equal to D over 2 minus TF over 2. And that's 400 over 2 minus 20 over 2. That gives us 190 millimeters. So the distance between the neutral axis and that force is the distance from the centroid of the shape. That's the elastic and plastic section or neutral axes are coincident. The centroid of the shape and the centroid of the flange. We can calculate YW as the distance between here and the middle of the web on top. And that will be equal to D minus 2TF over 2. So that will be the distance between here and the top and the bottom of the flange. And we need to further divide that by 2 to get the centroid. And this gives us 400 minus 20 times 2 divided by 2 times 1/2. And that is 90 millimeters. So now we have the magnitudes of the forces and their locations. And we can calculate the moment, the plastic moment. This gives us MP is equal to 2 times our flange force times Y flange plus 2 times our web force times Y web. So MP is 2 times 1400 times 10 to the 3 newtons multiplied by 190 millimeters plus 1260 times 10 to the 3 newtons multiplied by 90 millimeters. And our plastic moment is equal to 758.8 times 10 to the 6 Newton millimeters, which is 758.8 kilonewton meters. Now this will directly give us the section modulus. Zx is equal to MP over Fy. And that's equal to 758.8 times 10 to the 6 Newton millimeters divided by 350 MPa. And recall MPa is Newton per millimeter squared. So this comes out to the correct units of millimeters cubed. So Zx is equal to, well, let me write it down below. Zx is equal to 2168 times 10 to the 3 millimeters cubed. Let's put that in red. So we found our elastic moment, our elastic section modulus, our plastic moment, and our plastic section modulus, and all that's left is to compute our shape factor, which compares the two. So shape factor, K is equal to Z over S, and that's equal to 2168 times 10 to the 3 over 1639.7 times 10 to the 3, and that's equal to 1.32. So this is interesting. Interesting to note that when we get rid of a lot of the material that separates a I-beam or W shape from a rectangular shape, the area inside of the flanges there, that doesn't change the section modulus, or not the section modulus, I'm sorry, the shape factor all that much. We recall that a rectangular one had a shape factor of 1.5. So this is part of the reason why we use these W sections, or pretty much the predominant reason, is that they are tremendously efficient in terms of their area, which corresponds to their mass and corresponds to their cost, and also the load on the structure, as that's very efficient, a low area and a very high moment resistance, and also the high plastic moment resistance as well. So we don't see a tremendous loss in plastic capacity. And that's what makes these W sections or I-beams so efficient. So we've seen two videos now, or two examples, one of a rectangular section and one of an I-beam section, and both were doubly symmetric. The next video in this 3-video series will show what happens when we have a non-symmetric shape, in this case a T-beam. And this T-beam will experience something that we haven't seen here, which is a shift in the neutral axis once we move from elastic to plastic material properties.